some of the pre-questions that you wanted me to answer, there's a list there that will tell you whether this video is useful to you or not. So we'll start with 2020 12B. So this is the one. On a particular day, solar radiation falls on the surface at a rate of 850 watts per meter squared. That means 850 joules are shining on 1 meter squared every second. The next sentence says 52% of that is infrared radiation. So if we got 0.52 of the 850, that would tell me how much infrared radiation is shining per second on 1 meter squared of Antarctica. The next sentence, the average frequency of the infrared radiation is 15 terahertz. That's the frequency of one photon. So 15 tera is 15 by 10 to the power of 9 hertz. That's the frequency of one photon. So using E is equal to HF, we could get the energy of one photon. And the solar radiation would be made up of many, many photons. In fact, the energy here multiplied by the number of photons, so work out the energy from 15 terahertz, multiplied by N, which is the number of photons, will equal the amount of infrared radiation shining per second on 1 meter squared of the Antarctic surface. Okay, this one should be fairly straightforward. Conduction, convection, and radiation. Second, calculate the infrared radiation that falls on 0.25 meters squared of Antarctica in 3 minutes. So that's the amount that shines on 1 meter squared. Divide that by 4 to get the amount on a quarter of a meter. And a watt is a joule per second. So that's the amount per second. Multiply that by 180 to convert to minutes. Okay, the next part, calculate the number of infrared photons that fall on the area of this at this time. So you have the energy from the previous part. You can calculate the energy of one photon from this, and then you divide one by the other. Now I'll show you that done out. So 850 watts per meter, first line. Infrared radiation is 52% of that. And we're looking at the effect on a quarter of a meter. So I've got a quarter by 0.52 by 850. And then in 3 minutes I multiply by 180 and gives me roughly 19,500 joules. That's the total infrared energy shining on the designated area. For part 3, we're given a frequency. We calculate the energy. That's the energy of one photon, 9.9 by 10 to the minus 24 joules. So if we divide that number into the 19,500, we get the number of photons. I haven't done the calculation because I have no calculator. You can work away on that yourself. Okay, back to the second part. Calculate the energy required to melt 0.5% of the Earth's glaciers if their average temperature is -6 and the melting point is -2. So what's happening here is the glacier has to heat up from -6 to -2, and then it changes state at -2 degrees Celsius. So the energy required is going to be mc delta theta to change temperature by 4 degrees plus ml to change state. Now you'll notice that we're not given the mass at all, but we are given a volume there. We're given 0.5, so if we got 0.5 of that, that would give the volume that we're melting in the question. And because we're given volume, it makes sense that we'd be given density as well. So density as mass over volume will allow you to get the mass there. And then you have mc delta theta plus ml. So here we are again. Part 4, energy required is change in temperature and change of state. So we get two formula there in the box, add them together. We have the C values given, we have the L values given. Change in temperature is 4. I've calculated the mass from density by volume. You just sub it in and solve. And that's the first question done. Okay, the second question is from 2019, question 7. So it's this one, and specifically you wanted to know how to do the calculation part, which is here. Okay, actually this part. There's an electric field strength of 2.3 at a distance 0.05 meters from the surface of the conductor. Calculate the charge on the conductor. When you see electric field strength in distance, you're using the formula not in the log tables. E is 1 over 4 pi epsilon Q over d squared. The spherical conductor is 12 centimeters. I suppose the biggest mistake people make here is the diameter there is 0.12 meters. The particle is placed 0.05 meters away, and then what you need to do is get the distance to sub into the formula. which is the distance from the center of the sphere. So that's 0.11 meters. And when you sub it in, you'll get your value there as shown. Okay, the next question was 2018 question 11. I was unsure which parts you wanted me to do, but one of you did mention that you wanted to do D and E. So let me see. Question 11, D and E. So D is calculate the position of the image of a person when the U value is 0.75. And we're talking about the Leviathan mirror, and the Leviathan mirror has a focal length of 16. So it's quite clear here that the object distance is inside the focal length. So when you use 1 over f is 1 over u plus 1 over v, you will get a negative v value because it'll be a virtual image. When you do that, and we can see it here, 1 over 16 is equal to 1 over 0.75, remember your SI units, plus 1 over v, v works out as negative, and v is negative, so that means that the image is behind the mirror, just as you can see there in the diagram below it. Right. I'm also going to do G as well, because the calculations on that aren't very straightforward, so let's have a read of it. Calculate the velocity of the Hubble telescope as it orbits the Earth. So the Hubble telescope is a particular distance from the center of the Earth. It's 570 kilometers above the surface of the Earth. Add the 6400 kilometers, and that gives you the radius of its orbit. If you use pi r squared, you'll get the distance of the path that Hubble takes around the surface of the Earth. So it's the circumference of a circle, pi r squared. The next thing then is we need a time, because we're looking for the velocity being displacement over time. It undergoes that many orbits per day. So if it undergoes that many orbits per day, if you divide that by the time in a day, there we go. So 15.1 divided by that will give you the time, and then multiply by the distance, and job done. Now, last question was 12C, a capacitance question. Okay, define capacitance and state its unit. Put the notation in, and the unit is the farad. Second one, calculate the energy stored in the capacitor. So energy is a half CV squared. Sometimes you need to use C as Q over V and get your values via the 2 formula, but in this case, we have the C, we have 4,000 volts there, in which case you just sub it in, and you get a half by 0.11 by 16 by 10 to the 6. You can work it out. The next one is what's the net charge on the capacitor. If there's a positive plate and a negative plate and they have the same charge but of opposite signs, the net charge is 0. And then the last part, second last part, the capacitor discharges in 15 milliseconds. Calculate the average current flowing as the capacitor discharges. Well, that's the charge, that's the time, current discharge divided by time. You can work that out. And there's the electric field around the parallel plates.